Imagine you're standing on your rooftop in Mumbai, the city lights twinkling below. Or maybe you're sitting in your village courtyard out in Rajasthan, looking up at that vast, inky night sky. It's full of stars, right? Just countless pinpricks of light. But have you ever stopped to really wonder, what is the sky, actually? Is it like a giant ceiling, maybe, keeping everything in? Or maybe a huge canvas stretched out, painted with distant lights? Or is it something much bigger, something almost beyond comprehension? For thousands of years, brilliant minds from ancient India to the great thinkers of Greece have asked these very questions. They were trying to map the cosmos, figure it all out. Today, we're going on a bit of a cosmic journey, a real deep dive into the universe itself. We'll explore how our understanding, our picture of the cosmos has changed over centuries. We went from thinking Earth was the absolute center of everything to realizing we're just a tiny part of this huge expanding universe. And we even discovered these mind-bending, frankly weird objects like black holes. Our mission today really is to take this stack of fascinating, sometimes complicated ideas and make them simple, clear, and hopefully as exciting as, say, a T20 match, so that you, our curious listener, can feel truly clued in about the grandest story there is.
That's precisely our aim. We're not just, skimming the surface here. We want to dive deep into some really fundamental ideas about the universe's history and its most mysterious inhabitants. We'll start by tracing that fascinating story of how humanity's ideas about the universe evolved. What did people believe about the Earth, the stars? And how were those ideas challenged, tested, and quite often completely overturned? Then we'll shift gears to a truly revolutionary idea. That the universe isn't static. It's not like some massive, unchanging monument. It's actually expanding, getting bigger every single second. And this incredible realization, it leads us directly to the Big Bang, the universe's very beginning. The moment time itself is thought to have kicked off. Finally, we'll explore those enigmatic cosmic vacuum cleaners, black holes. We'll try to understand how they form, usually from the fiery death of massive stars, what they fundamentally are, and maybe touch on why they're not quite as black as the name suggests, at least theoretically. It's going to be a journey filled with surprising facts, some amazing deductions, and hopefully plenty of those aha moments. It really shows how science is constantly questioning, exploring, and revising its understanding of everything around us. It's always pushing the boundaries of what we thought was possible.
Okay, let's unpack this cosmic history then, starting right at the beginning of human curiosity. For a very long time, it seems, many cultures believed the Earth was flat, like a giant dosa maybe, or a big flat chapati. The idea being if you travel too far, you might just fall off the edge. But even surprisingly early on, people started to figure out that wasn't quite right. What were the first hints? What observations suggested around Earth?
Indeed. And it was surprisingly early. As far back as 340 BC, a brilliant Greek thinker, Aristotle, he wasn't just guessing, he was observing the natural world really carefully. He noticed something during lunar eclipses, when the Earth passes between the sun and moon. He saw that Earth's shadow cast on the moon was always round.
Always round.
Consistently round. Now think about it. If the Earth were a flat disk, its shadow would usually look like a long stretched oval, wouldn't it? Unless the sun was exactly overhead, maybe.
Right.
But a consistently round shadow that strongly points towards a spherical Earth. It's a pretty powerful piece of visual evidence, something anyone could potentially observe.
That makes perfect sense when you put it like that. Simple observation, big conclusion. And wasn't there also something about how stars appeared when you traveled north or south?
Yes, exactly. Imagine taking a long journey, say, from Kanyakumari, right at the southern tip of India, all the way up to Jammu and Kashmir in the north. If you observe the North Star, the pole star, it seems fixed in the sky, right? You'd notice it appears higher in the sky the further north you go.
Oh, okay.
Aristotle used this very difference in apparent position to even try and estimate the Earth's circumference. Now, his estimate was about twice the actual size, quite a bit off.
It's still pretty amazing for the time.
Absolutely. The fact that he's making such calculations based on observation, it shows incredible foresight, a foundational understanding of a spherical world derived from looking up.
And what about ships at sea, approaching the shore? That's another classic example they teach, isn't it?
It is another great piece of observational evidence used by the Greeks. They noticed that when a ship approached from the horizon, you'd first see its mast and sails just peeking over the curve.
Right, the highest part first.
Exactly. And only later, as it got closer, would you see the hull, the main body of the ship.
Whereas if the Earth were flat,
You'd see the whole ship at once, wouldn't you? Just
Yeah.
getting bigger and bigger as it sailed closer. This sails first, then hull observation strongly suggested a curved surface. The lower parts of the ship were hidden by the Earth's bulge until it got nearer.
so even thousands of years ago, people had really solid evidence the Earth was a ball, not a plate. Which makes it even more remarkable, doesn't it, that despite this strong evidence for a spherical Earth, the idea of Earth being the center of everything lasted for so incredibly long.
Yeah.
What made that geocentric idea so sticky?
That's a really great question because it highlights the power of, well, ingrained beliefs and maybe wishful thinking. Despite recognizing Earth was a sphere, Aristotle and many others felt Earth had to be the universe's unmoving center. They had what they considered sort of mystical reasons or philosophical ideas about perfection. They believed everything in the heavens moved in perfect circles around us because circles were seen as the most perfect divine form of motion.
So it was less about pure observation and more about philosophy almost.
A mix, perhaps.
Yeah.
This idea was then refined and made much more mathematically complex by Ptolemy around the 1st century AD. His model, with Earth locked firmly at the center, surrounded by these crystal spheres carrying the moon, the sun, the known planets, Mercury, Venus, Mars, Jupiter, Saturn.
The ones you can see easily.
Right, and then the fixed stars on the outermost sphere. This model became the dominant view for incredibly over 1,400 years.
Wow, so it was like a gigantic cosmic Matryoshka doll with Earth as the tiny most important doll right in the middle.
Precisely. But it wasn't simple. To explain why the planets sometimes seem to wander backwards in the sky, they're sort of wobbly, non-circular paths.
Retrograde motion, they call it.
Exactly, retrograde motion. To explain that, Ptolemy had to add smaller circles on the main circles. They called them epicycles. Imagine a marble rolling around the rim of a spinning tholy, and then that tholy is also spinning on a larger table.
Okay, that sounds incredibly complicated.
It was like trying to untangle a really complex knot of kite strings after a big kite festival, maybe in Gujarat.
Yeah.
A real mess mathematically. And it had obvious flaws, too. For instance, his model predicted that the moon should sometimes appear twice as big as other times, which clearly doesn't happen. We'd notice that.
Yeah, definitely.
Yet, it was widely accepted. Partly because it was so detailed, it could predict planetary positions reasonably well for the time. And also, crucially, its structure was adopted by the Christian church in Europe. It fit neatly with theology, leaving ample room outside the outermost sphere for concepts like heaven and hell. It provided a comforting sense of order and affirmed Earth's, and therefore humanity's, central importance in the divine plan.
So Ptolemy's super complicated. Earth at the center model lasted for ages. Who was the brave soul who finally dared to say, hang on, maybe this isn't right? Who shifted Earth out of that cosmic spotlight?
Well, the big shift began in 1514 with a Polish priest named Nicholas Copernicus. He proposed a much simpler, much more elegant idea. The sun was stationary at the center, and Earth, along with the other planets, orbited it in circular paths.
Simpler sounds better, but he published it anonymously.
Yes, at first. He feared accusations of heresy, going against religious doctrine and centuries of accepted wisdom. The Earth-centered view was so deeply entrenched, it was a truly radical thought for its time.
Understandable fear, I suppose. And it took nearly a century for his idea to be taken seriously. That's a long wait for a revolution.
It is. What finally convinced people, or at least started the ball rolling, were two other astronomers. Johannes Kepler, a German, and Galileo Galilei, an Italian. They became strong public supporters of Copernicus's sun-centered or heliocentric model. But the real game changer, the knockout blow for the old model, came in 1609. Galileo got his hands on a newly invented telescope.
Ah, the telescope.
Exactly. He started observing the night sky with unprecedented detail, and when he pointed it at Jupiter, he made a stunning discovery. He saw that Jupiter had several small moons orbiting it. not Earth.
Moon's orbiting another planet, wow.
It was huge, undeniable proof that not everything revolved around Earth. It was a massive blow to that core assumption of the Earth-centered model. It showed celestial bodies could definitely orbit centers other than Earth.
So Jupiter's moons were like little mini solar systems in a way, showing that not all the smaller lights in a massive wedding celebration revolve around the main stage. Some are clearly circling around smaller decorations. That must have been a truly profound moment. But even Copernicus, with his sun-centered model, he still thought the orbits were perfect circles, didn't he? That part was still wrong.
That's a sharp observation. You're absolutely right. Galileo provided the observational proof against geocentrism, but the problem of the perfect circular orbits remained. Copernicus stuck with circles. It was Kepler who tackled that. Through incredibly meticulous calculation, analyzing years of observational data, he realized the planets didn't move in perfect circles. He initially found the idea repugnant, apparently, because circles were considered the most perfect divine shape.
So he didn't like it, but the data forced his hand.
Pretty much. He realized the planets moved in ellipses, sort of stretched circles, oval shapes. This crucial modification, moving away from perfect circles, finally made the predictions of the sun-centered model match the actual observations of planetary motion with remarkable accuracy. It was a compromise with philosophical perfection, maybe, but a huge triumph for observational science.
Okay, so Kepler fixed the how the planets move in ellipses around the sun. But he didn't really explain the why, did he? What force kept them in these specific elliptical paths? Why did they stay in orbit at all and not just fly off into space?
Exactly. That crucial why question brings us to the monumental figure of Isaac Newton. In 1687, he published his groundbreaking work, Philosophiae Naturalis Principia Mathematica, usually just called the Principia, this book. Well, it's considered one of the most important single scientific works ever published. Newton didn't just describe how bodies moved, he developed the precise mathematics needed to analyze those motions, calculus, essentially. And crucially, he proposed the universal law of gravitation.
Ugh! The apple story. We all hear that one in school, right? The apple falls from the tree, hits him on the head maybe, and boom, gravity.
Well, the story of an apple literally hitting his head is probably just a nice bit of folklore, a legend. But the core idea behind it is true. Newton had this profound insight. The same force that pulls an apple down to the ground is also the force that keeps the moon orbiting the Earth and the planets orbiting the sun. It wasn't two different sets of rules.
One force for everything.
One universal force. His law stated that everybody in the universe attracts every other body. This attraction is stronger if the bodies have more mass, and it gets rapidly weaker the farther apart they are. It was this unified theory of motion that applied equally to apples on Earth and planets in the heavens.
So it's kind of like maybe the more people there are packed into a Durga Puja Pandal during the festival, and the closer they are bunched together, the stronger the pull of a crowd feels. You can almost feel that collective gravitational force trying to pull you in.
That's a truly great analogy. It captures that sense of collective pull. Newton's theory completely did away with Ptolemy's complicated celestial spheres that just weren't needed anymore. And with them, the idea that the universe had some fixed, hard boundary also disappeared. The fixed stars weren't stuck on a sphere. They were now understood to be objects like our own sun, just much, much farther away. That's why their positions didn't seem to change much as Earth orbited the sun.
Okay, so the universe is bigger, maybe infinite, filled with suns, but this raised a huge new problem, didn't it? Newton himself realized this, right?
He did. If his theory of gravity was right, and every star attracts every other star, well, shouldn't they all eventually fall together? Why hadn't the universe collapsed into one giant clump already?
Yeah, it sounds like a cosmic traffic jam just waiting to happen. If gravity's always pulling, always attractive, why isn't the universe just one massive collapsed blob?
It's a significant puzzle. Newton himself wrestled with it. He suggested, maybe, that if there were an infinite number of stars, distributed more or less uniformly throughout infinite space, then there wouldn't be any single central point for them all to fall towards. The pulls would kind of balance out in all directions.
An infinite balance.
Sort of. However, as people realized later, this argument doesn't quite hold up. In an infinite universe, any point could be considered the center. And if you just think about a finite region of stars, even a huge one, they would still collapse inwards under their mutual gravity. Adding more stars infinitely far outside that region wouldn't stop the initial collapse within it. So, the key insight here, which took a long time to sink in, is this. It seems impossible to have an infinite static model of the universe where gravity is always attractive, a universe that just sits still, unchanging forever. It's fundamentally unstable according to Newton's own laws.
Wow, that's a profound shift in thinking. For centuries, the idea of an eternal, unchanging universe was probably quite comforting, wasn't it? Even if people aged and died, the cosmos felt permanent.
Exactly. There was a deep-seated philosophical preference for an unchanging universe. So even when people saw that Newton's theory seemed to imply instability, they didn't immediately jump to the idea of an expanding or contracting universe.
What did they try instead?
Well, some tried to modify Newton's theory. They suggested maybe gravity becomes repulsive at very large distances, somehow balancing out the attractive forces over shorter distances. But we now believe such an equilibrium would be inherently unstable, like balancing a pencil perfectly on its point, the slightest nudge, and it falls over.
So if stars got a tiny bit too close, they'd still collapse. A tiny bit too far, they'd fly apart.
Precisely, it wouldn't be a stable fix. And then there's another nagging problem related to an infinite, static, eternal universe. Olber's paradox.
Olber's paradox. I've heard of this. It's the question about why the night sky is dark, right? If there are infinite stars, shouldn't the whole sky be blazing bright, even at night?
That's exactly it. Named after Heinrich Olbers, though others had thought about it too. If the universe were infinite in space, filled with stars that have been shining forever, then basically every line of sight from Earth should eventually end on the surface of a star.
Like looking into an infinite forest eventually, your line of sight hits a tree trunk.
Perfect analogy. In that scenario, the entire night sky should be as bright as the surface of the sun, which clearly it isn't. Olbers himself tried to suggest maybe intervening dust or gas absorbed the light.
But wouldn't that dust just heat up and glow itself?
Exactly. Eventually, that intervening matter would heat up so much it would glow just as brightly as the stars themselves. The only real way out of this paradox is if the stars haven't been shining forever. Or, crucially, if their light simply hasn't had enough time to reach us yet because the universe isn't infinitely old. This strongly hinted that the universe must have had a beginning.
So this idea of a beginning for the universe, it wasn't entirely new then. Many religious texts, ancient traditions thinking about stories from India or the Abrahamic faiths, they often talk about creation, right? A specific point in time when everything came into existence.
Correct. Many ancient cosmologies across different cultures proposed a beginning at some finite time in the past. One common argument was the philosophical need for a first cause. Something had to start everything. St. Augustine, a hugely influential Christian philosopher, even made a kind of logical argument. He suggested that if humanity and the universe had been around literally forever, we would surely have progressed far, far more than we had. We'd know everything, achieved everything.
An interesting thought.
He accepted a creation date of around 5000 BC based on biblical interpretation, which is, interestingly, quite close to when organized human civilization really began to flourish after the end of the last ice age.
But the ancient Greeks, like Aristotle, they thought the universe was eternal, no beginning.
Yes, generally they disliked the idea of divine intervention creating everything at a specific moment. They countered Augustine's progress argument by suggesting maybe periodic floods or other huge disasters repeatedly wiped the slate clean, resetting human civilization. So for a very long time, the question of whether the universe had a beginning was really a matter for philosophy or theology, not so much for science. You could find arguments and observations to support either view.
But then something truly massive happened, a discovery that shifted this whole conversation from philosophy into the realm of hard science, of observation and measurement.
Yes. The truly revolutionary shift came in 1929. An American astronomer named Edwin Hubble, using the powerful new telescopes available then, made a landmark observation. He found that wherever you looked in the sky, distant galaxies, these massive islands of stars outside our own Milky Way, they were all moving rapidly away from us.
Not just some, but all of them.
All the distant ones he could measure. It wasn't just a random scattering, it was a universal phenomenon. This was the undeniable, frankly earth-shattering discovery. The universe is not static. It is, in fact, expanding.
Expanding. So the universe isn't like a massive, unchanging monument or a grand still painting. It's actually stretching, getting bigger all the time. That's just mind-boggling to try and visualize. How did he even figure that out?
Well, to understand this, we need to take a quick step back. Our sun and all the stars we see easily at night, they're part of our home galaxy, the Milky Way. For a long time, people thought that was the entire universe. But in 1924, just a few years earlier, Edwin Hubble himself had proved definitively that ours was not the only galaxy. There were, in fact, countless other island universes, as they were sometimes called, separated by unimaginably vast stretches of mostly empty space.
Okay, so first he proved other galaxies exist. Then he needed to know how far away they were.
Exactly. To understand their motion, he first needed to measure their distances. And how do you measure something that's so incredibly far away? It's like trying to gauge the distance to a tiny lamppost on the horizon you can barely even see, let alone a whole galaxy millions of light years away.
Seems impossible.
He used indirect but very clever methods. He discovered certain types of stars, called Cepheid variables, whose brightness changes over time in a very predictable way. Crucially, the rate at which they pulsed was directly related to their true brightness, their intrinsic luminosity.
Like knowing a light bulb is definitely 100 watts, even if it looks dim from far away.
Precisely. So if he found one of these Cepheid standard candles in another galaxy, he could measure how fast it was pulsing to know its true brightness. Then he'd measure how bright it appeared from Earth. Comparing the two allowed him to calculate its distance. It was like having a cosmic measuring tape.
A cosmic measuring tape built from pulsating stars.
Yeah.
Brilliant. Okay, so we measured the distances. And then came the truly peculiar part, the redshift, which really nailed the idea of expansion. What exactly is that?
Right, the redshift was key. To understand it, think about sound waves first. Imagine an ambulance siren. As the ambulance races towards you, the siren sounds higher pitched, right? The sound waves are getting squished together.
Yeah, the high-pitched whine.
Then, as it passes you and moves away, the pitch suddenly drops, sounds lower. That's because the sound waves are being stretched out. This change in pitch due to motion is called the Doppler effect for sound.
Okay, I get that. Like on a busy street in Delhi, you hear that pitch change all the time.
Exactly. Well, light waves behave in a similar way. If an object emitting light, like a galaxy, is moving away from us, the light waves it emits get stretched out. Stretched light waves shift towards the red end of the visible light spectrum. We call this a redshift.
And if it were moving towards us?
Then the light waves would be squished, shifting towards the blue end, a blue shift. So, in the 1920s, astronomers started analyzing the light, the spectra from these distant galaxies Hubble had identified.
Yeah.
And they found something astonishing. Nearly all of them were redshifted.
All moving away.
Every distant galaxy they measured was moving away from us. And even more surprisingly, in 1929, Hubble published his most famous result. The farther away a galaxy was, based on his standard candle measurements, the faster it was moving away from us. There was a direct relationship.
Wow. So it wasn't just random movement. The whole system is expanding.
That was the unavoidable conclusion. It wasn't like galaxies were just flying through a static space away from us. It was the very fabric of space-time itself that was expanding, carrying the galaxies along for the ride like raisins baked into an expanding loaf of bread. This was the undeniable proof the universe was expanding.
Incredible. So Hubble found the observational proof the universe was expanding. But could anyone have actually predicted this beforehand, just based on theory? Was it hiding in the math somewhere?
Astonishingly, yes. And this is where it gets really interesting. Albert Einstein himself, when he first formulated his general theory of relativity back in 1915, our modern theory of gravity, he actually believed the universe had to be static. It just felt right philosophically. In fact, his original equations actually seem to predict a dynamic universe, one that should be expanding or contracting. He disliked this so much, he actually added an extra term to his equations, the cosmological constant, basically a kind of cosmic fudge factor, an invisible anti-gravity force, just to force his model universe to stay still.
He fudged his own theory to keep the universe static.
Essentially, yes. He later famously called this his biggest blunder, especially after Hubble's discovery proved the universe wasn't static. Though ironically, something like his cosmological constant has made a comeback in modern cosmology to explain accelerating expansion, but that's a whole other deep dive. But while Einstein was trying to force a static universe, a Russian physicist and mathematician named Alexander Friedman took Einstein's original equations, without the fudge factor, at face value.
So Einstein tried to make the universe static, but Friedman said, hang on, your own original theory tells us it must be dynamic.
Exactly. In 1922, several years before Hubble's observational discovery, Friedman worked out solutions to Einstein's equations that described an expanding universe. He started with just two fairly simple assumptions. First, that the universe looks essentially the same in whichever direction we look isotropic, and second, that this would also be true if we were observing the universe from any other point within it homogeneous. Basically, that the universe is roughly the same everywhere and in every direction on large scales.
Okay, the looks the same in every direction part. That seems a bit hard to believe from here on Earth, doesn't it? We see the bright band of the Milky Way across the sky. Stars aren't scattered perfectly evenly. It doesn't look uniform.
That's absolutely true on a local scale, within our own galaxy. Our view is lumpy. But Friedman was thinking on the largest possible scales. And if you look far beyond our galaxy, the distribution of distant galaxies, they do appear to be spread out remarkably uniformly across the sky. There's no preferred direction on that grand scale. What's even more fascinating is that Friedman's first assumption that the universe looks the same in all directions was accidentally and spectacularly confirmed much later, in 1965. Two American physicists, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were trying to develop a very sensitive microwave detector, initially for satellite communications. But they kept picking up this annoying background noise, a persistent, faint hiss in their detector.
Like static on an old radio, but it was coming from space. They must have thought their equipment was faulty at first.
They absolutely did. They tried everything to get rid of it. They checked all their systems, recalibrated everything. They even famously cleaned out pigeon droppings from inside their large horn-shaped antenna, thinking maybe that was causing the interference.
Pigeons causing cosmic static. That's brilliant.
But the noise persisted. It was faint, but it was definitely there. And crucially, it seemed to be coming equally from every direction in the sky, day and night, season after season, no matter where they pointed their antenna. They eventually realized they had stumbled upon something monumental. This mysterious noise was the cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang.
Precisely. It's the leftover heat, the faint radiation echo from the incredibly hot, dense state of the very early universe, just a few 100,000 years after the Big Bang. Its remarkable uniformity across the entire sky was incredibly powerful confirmation that, on the largest scales, the universe is indeed extremely isotropic, the same in all directions, just as Friedman had assumed decades earlier. Penzias and Wilson won the Nobel Prize for this accidental yet absolutely epoch-making discovery. The CMB gives us a direct snapshot of the early universe, confirming it was once a hot, dense soup, which is exactly what a Big Bang predicts.
What an amazing story of accidental discovery, leading to profound insights about the universe's origins. Okay, so Friedman's models, based on Einstein's theory and confirmed by the CMB, predicted expansion. Did they also say what happens next? Does it expand forever? Or does it eventually stop and maybe collapse back in on itself, like a giant cosmic balloon deflating?
That's the crucial question Friedman's models addressed. His solutions actually describe three main possible fates for the universe, and which fate awaits us depends critically on the universe's average density, basically, how much stuff, matter, and energy is packed into it on average. More stuff means more gravity. So the first possibility is what we might call the collapsing universe. If the universe has a very high average density, lots and lots of matter packed in, then the mutual gravitational attraction between everything will eventually be strong enough to overcome the initial expansion. Gravity wins. In this scenario, the expansion would slow down, stop, and then reverse. The universe would start contracting, pulling all the galaxies back together, getting hotter and denser, perhaps ending in a big crunch, a sort of mirror image of the Big Bang.
Like throwing a cricket ball straight up in the air. If you don't throw it fast enough, gravity pulls it back down to Earth.
Exactly like that. That's scenario 1. Scenario 2 is the expanding forever universe. If the universe's average density is very low, not much stuff per unit volume, then gravity isn't strong enough to ever halt the expansion. The initial outward push is too strong. In this case, the galaxies will just keep flying apart forever. The expansion might slow down a bit due to gravity, but it never stops or reverses. The universe just gets bigger, colder, and emptier indefinitely.
Like firing a rocket from Earth really fast,
Yeah.
faster than escape velocity. It just keeps going, never falls back.
Precisely. Faster than about 11.2 kilometers per second, or 7 miles per second from Earth's surface. That's scenario 2. Finally, there's a fascinating borderline case. The just right universe, sometimes called the critical or flat universe. This happens if the average density is exactly at a specific critical value. In this model, the universe expands just fast enough to avoid collapsing back on itself, but only just barely. The speed of expansion gets slower and slower and slower over infinite time, approaching zero but never quite reaching it. It expands forever, but at an ever-decreasing rate.
So, like throwing the cricket ball just hard enough that it slows down endlessly but never quite falls back down. It just hangs there, asymptotically approaching a stop.
That's the idea. 3 possible cosmic destinies.
Okay, so which one are we in? Are we headed for a fiery big crunch, eternal lonely expansion, or this just right scenario? Do we know?
That is the multi-billion-dollar question in cosmology. It's what scientists are actively working on right now. We can measure the universe's current expansion rate quite accurately using Hubble's law and the Doppler effect, redshift, on distant galaxies in supernovae. However, measuring the universe's average density accurately is much, much harder. We can count the stars and galaxies we see, sure, but we now know that visible matter makes up only a tiny fraction of the universe's total mass and energy content.
Right, dark matter and dark energy. The invisible stuff.
Exactly. There's a huge amount of dark matter that we can't see directly, but we know it must exist because we can detect its gravitational pull on the visible matter. It's like knowing a very heavy invisible hand is shaping how galaxies rotate and cluster together. And even more mysteriously, there's dark energy, which seems to be causing the expansion of the universe to accelerate, not slow down. But when we try to add up all the visible matter, the inferred dark matter, and the estimated dark energy...
What's the verdict? Enough to stop the expansion?
Well, based on our best current measurements, even including all the dark matter we think is there, it still seems to be significantly less than the critical density needed to eventually halt the expansion and cause a big crunch.
So it looks like we might be in the expanding forever camp, possibly even accelerating, not the collapsing one.
That's currently the prevailing view, yes. The evidence we have right now strongly suggests our universe will likely expand forever, and maybe even at an accelerating rate due to dark energy. But, and this is crucial, science is always refining its understanding as new data comes in, new telescopes get built, new theories are tested. Our picture could change. However, even if the universe were destined to recollapse eventually, the calculations show it wouldn't happen for at least another 10,000 million years. Probably much longer.
10 billion years. Okay, so not something to lose sleep over tonight. That's a time scale so vast it just dwarfs human history, or even the age of the Earth.
Absolutely. By then, humanity's future, if we're still around, would likely involve other planets, maybe other star systems, or perhaps forms of existence we can't even imagine now.
Okay, so all these expanding universe models, whether they expand forever or eventually collapse, they all seem to point backwards in time, don't they? To a specific moment when everything was incredibly close together. This is what we call the Big Bang, right? The moment it all began.
Yes, that's precisely it. All of Friedman's solutions, based on general relativity, have this inescapable feature. If you run the clock backwards following the expansion in reverse, there must have been a time in the past, currently estimated to be around 13.8 billion years ago, when the distance between any two neighboring galaxies was effectively zero. At that point, the moment we call the Big Bang, the density of the entire universe and the curvature of space-time would theoretically have been infinite. This mathematical point of infinite density and curvature is what we call a singularity.
Infinite density. That sounds completely unbelievable. It's hard to even wrap your head around. Like trying to squeeze all the people in India, more than 1 billion of us, into a single tiny village. The numbers just don't compute.
They don't, and you're right to find it mind-boggling. Our current scientific theories, including general relativity and quantum mechanics as we understand them, are formulated on the assumption that space-time is smooth and relatively flat on small scales. They simply break down at the extreme conditions of a singularity. The maths gives infinite answers, which usually means the theory is incomplete. This means we can't use our current laws of physics to reliably describe or predict anything at or before the Big Bang singularity. As far as our current science is concerned, time itself effectively had a beginning at the Big Bang.
So before the Big Bang is meaningless.
From a scientific perspective based on these models, yes. Any hypothetical events before this singularity couldn't causally affect what happened afterward, because predictability breaks down completely there. So scientifically, it makes sense to say that time, as we measure and understand it, began then.
This idea of time itself having a definite beginning, it does feel a bit like those religious creation stories we mentioned earlier. And some people might find that uncomfortable in the realm of science, which often tries to explain things without needing a first cause or a specific creation moment outside the system.
That's a fair point, and it's true that the Big Bang model does align with some religious views of creation. Historically, the Catholic Church, for instance, officially acknowledged the Big Bang theory's compatibility with the Bible back in 1951, seeing it as evidence for a moment of creation. However, it's really important to stress that the scientific reason for accepting a beginning in an expanding universe isn't based on theology. It's a physical necessity that arises directly from applying Einstein's general relativity to the observation that the universe is expanding. It's derived from observations and mathematical theory. It simply means that asking what happened before the Big Bang might be like asking what's north of the North Pole. Within the framework of the model, the concept itself might be ill-defined. It does place limits, in a sense, on when a hypothetical creator might have carried out their work, if one assumes there was one.
Right. It arose from the physics, not from trying to fit a religious idea. So was the Big Bang immediately accepted, or were there alternative scientific ideas trying to avoid this singularity, this beginning? I've heard of the steady-state theory.
Yes, the steady-state theory was a major competing idea for a while. Proposed in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle, who ironically coined the term Big Bang somewhat mockingly, it was a serious attempt to avoid a beginning. Their idea was clever. Yes, the universe is expanding and galaxies are moving apart, but perhaps, they suggested, new matter was continuously being created out of nothing in the empty space between the galaxies. This new matter would then form new stars and new galaxies, filling in the gaps as the older ones moved away.
So the universe would look roughly the same at all times, eternally regenerating itself.
Exactly. The universe would be expanding, but its overall density and appearance would remain constant over time, hence steady state. It was an elegant idea, and importantly, it was a good scientific theory because it made clear, testable predictions.
What did it predict?
For instance, it predicted that the universe should look the same everywhere and at all times. So if you looked at very distant galaxies, which, because light takes time to travel, means you're looking back in time, they should look statistically the same as nearby galaxies. The number and type of galaxies per unit volume should be constant.
And was that true?
No. Observations, particularly surveys of distant radio sources in the late 1950s and early 1960s, started to contradict this. They found that there seemed to be more powerful radio sources, like quasars, in the distant early universe than there are nearby, closer to the present day. This suggested the universe was changing over time, evolving.
The universe looked different in the past. Bad news for steady state.
Very bad news. And then the discovery of the cosmic microwave background radiation by Penzias and Wilson in 1965 was really the final nail in the coffin for the steady state theory.
Why was the CMB so definitive?
Because the CMB is direct evidence that the universe was much, much hotter and denser in the past. A universe that was once a blazing hot fireball is completely incompatible with the steady state idea of a universe that's always looked roughly the same. The CMB was predicted by Big Bang theorists like George Gamow and colleagues decades earlier, but its discovery provided incredibly strong proof for the Big Bang model and against steady state. Reluctantly, the steady state proponents had to abandon their theory.
So the Big Bang won the scientific debate. But people still didn't like that singularity idea, right? That point of infinite density.
Correct. There were still attempts, even within the framework of general relativity, to see if the singularity could be avoided. Maybe Friedman's models were too simplified, too perfectly smooth and uniform. Some scientists, like two prominent Russians, Lifshitz and Kalatnikov, argued that the real universe, with all its lumps and bumps and sideways galactic motions, might be messy enough to avoid collapsing perfectly to a single point. Maybe it could sort of miss the singularity or perhaps bounce back from a previous contracted phase without hitting infinite density.
A messy universe avoids the crunch point.
That was the hope. They worked for years on complex calculations and initially thought they had proved that a singularity could be avoided in more general, less perfect models. However, they later realized their conclusion was mistaken. They found that even more general models, closer to the real universe, still seemed to lead inevitably to singularities under plausible conditions.
So the singularity seemed unavoidable, even in messy models.
It appeared so. But the truly crucial theoretical work came from Roger Penrose in 1965, and later from a highly influential joint paper by Penrose and Stephen Hawking in 1970. They used powerful new mathematical techniques within general relativity. They proved, quite rigorously, that if general relativity is correct, and if the universe contains as much gravitating matter and energy as we observe, which it seems to, then there must have been a Big Bang singularity in our past. Their theorems showed that under very general conditions, gravity is strong enough to inevitably lead to a singularity when tracing the expansion backwards.
So the math was undeniable.
The mathematical proofs were very robust and widely accepted, although the physical interpretation of the singularity itself remains a major area of research, likely requiring a theory combining gravity and quantum mechanics. But the conclusion that our universe, as described by general relativity, had a beginning in time became scientifically mainstream.
Okay, so from the very beginning of the universe, the Big Bang, let's fast forward billions of years to some of its most bizarre, most extreme creations. Black holes. Just the name, black hole, it sounds like something straight out of science fiction, a cosmic monster lurking in the dark.
It really does, and the term itself is actually quite recent. It was coined only in 1969 by the American theoretical physicist John Wheeler. He was known for his catchy phrases. But the underlying idea is much older, going back over 2 centuries, surprisingly. As far back as 1783, a Cambridge scholar, a geologist actually, named John Michell, was thinking about Newton's theory of gravity and his theory of light, which Newton thought was made of particles. Michell wondered, what if a star was so incredibly massive and also so compact, so dense, that its escape velocity, the speed needed to escape its gravity, was greater than the speed of light itself?
Escape velocity greater than light speed.
Exactly. If light particles couldn't travel faster than the speed of light, then even light emitted from the surface of such a star would be pulled back by the star's immense gravity before it could get very far. The star would be invisible.
A dark star. You couldn't see it, but you'd still feel its immense gravitational pull if you got close, like a very heavy, invisible boulder sitting on a cosmic road that you can't see, but you'd certainly feel its presence if you tried to move past it.
That's a perfect way to think about it. And interestingly, a few years later, the famous French scientist Pierre-Simon Laplace made a very similar suggestion independently in his work. So the concept of these dark stars, what we now call black holes, was floating around based just on Newtonian ideas. However, a full, consistent understanding of how gravity really affects light, especially its constant speed, had to wait for Einstein's general theory of relativity in 1915. Newtonian gravity wasn't quite equipped to handle light properly in such extreme situations.
Okay, so the idea was old, but Einstein's theory was needed to really understand them. How does a normal star actually become one of these incredible light-trapping black holes? What's the cosmic process?
It all comes down to the life cycle of a star, which is this beautiful, dramatic cosmic dance of creation and eventual destruction, driven by gravity and nuclear physics. A star is born when a huge cloud of gas, mostly hydrogen and helium left over from the Big Bang, starts to collapse in on itself due to its own gravitational attraction. As the cloud contracts, the gas atoms collide more frequently and it heats up. A lot. Eventually, the core of this collapsing cloud gets so incredibly hot and dense that hydrogen atoms start to fuse together. They overcome their natural repulsion and merge to form helium atoms. This process is called nuclear fusion.
Right, so a star is basically a gigantic, naturally occurring nuclear fusion reactor, like a continuous, controlled hydrogen bomb, releasing all that incredible heat and light energy we see.
Precisely. It's a massive fusion furnace. The enormous heat generated by this fusion creates a powerful outward pressure. Gas wants to expand when heated, right? This outward thermal pressure pushes against the inward crush of gravity. For most of a star's life, these two forces are in a delicate balance. Gravity pulls in, fusion pressure pushes out. This keeps the star stable and shining steadily for billions of years. Our own sun is a great example of this stable balance right now.
So a star is this giant balancing act.
Yeah.
Gravity pulling in, nuclear fire pushing out. What happens when the fire starts to die down? When the star runs out of its nuclear fuel? That must be a pretty dramatic end to the balance.
It is. Eventually, every star exhausts the hydrogen fuel in its core. Then it might start fusing helium into heavier elements like carbon and oxygen, and then maybe even heavier elements if it's massive enough. But eventually, the fuel runs out. And here's a paradox. The more massive a star is, the faster it burns through its fuel. Seems counterintuitive, but...
More fuel means it burns faster. Why?
Because a more massive star has a much stronger gravitational pull trying to crush it. To counteract that stronger gravity and maintain the balance, its core needs to be much hotter and denser, which means the nuclear fusion reactions run at a much faster rate. So while our sun has enough hydrogen to last for about 10 billion years in total, it's about halfway through now, a star just 10 times more massive might burn through its fuel in only a few tens of millions of years.
Wow. Live fast, die young for massive stars. Okay, so when the fuel finally runs out, the fusion stops. What happens then? Gravity takes over.
Gravity takes over completely. With the outward pressure from fusion gone, there's nothing left to resist the relentless inward pull of gravity. The star begins to collapse catastrophically under its own weight. What happens next depends crucially on the star's mass.
And this is where a truly remarkable Indian scientist made a pivotal contribution, right? Calculating a critical limit for what happens to these collapsing stars.
Indeed. This is a fantastic story in science. In 1928, a brilliant young Indian graduate student named Subramanian Chandrasekhar was sailing from India to England to study physics at Cambridge with Sir Arthur Eddington. During that long sea voyage, he started doing some incredible theoretical calculations about the fate of stars after they run out of fuel. He worked out the maximum mass a star could have and still be able to support itself against its own gravity once its nuclear fires died out. This fundamental limit became known as the Chandrasekhar limit.
How did he figure that out? What force could possibly resist gravity's final crush?
He used principles from the then new theory of quantum mechanics, specifically something called the Pauli exclusion principle. This principle, applied to electrons, essentially says that no two electrons can occupy the exact same quantum state, same position, same velocity, simultaneously. As the star collapses and electrons get squeezed incredibly close together, this principle forces them to move around with very different, very high velocities. This rapid motion of electrons creates a powerful outward pressure called electron degeneracy pressure. It's a purely quantum mechanical effect resisting further collapse.
So it's like trying to squeeze all the people from a huge cricket stadium like Eden Gardens into a tiny classroom. They simply can't all be in the same space doing the same thing. They have to keep moving and pushing outwards.
That's a great analogy. For stars with relatively low mass, like our sun, this electron degeneracy pressure is strong enough to eventually halt the gravitational collapse. The star settles down into becoming a white dwarf, an incredibly dense object, about the size of the Earth but containing the mass of a star. A teaspoonful would weigh many tons, but it's stable. If the star is a bit more massive, the collapse might crush electrons and protons together to form neutrons, creating an even denser neutron star, also supported by a similar quantum pressure, neutron degeneracy pressure. However, Chandrasekhar's crucial insight, combining quantum mechanics with Einstein's special relativity, was realizing there's a limit to how much resistance this degeneracy pressure can provide. Relativity dictates that particles can't move faster than the speed of light. As the star gets more massive and collapses further, the electrons, or neutrons, would need to move faster and faster to provide enough outward pressure. He calculated that if the mass of the cold, collapsing stellar core was more than about 1.4 to 1.5 times the mass of our sun, the exact value depends slightly on composition, then even this quantum degeneracy pressure would fail. Gravity would inevitably win. That mass threshold is the Chandrasekhar limit.
Wow. So for stars whose leftover cores are heavier than this Chandrasekhar limit, what actually happens to them? Does gravity just crush them out of existence? And how did the scientific community react to such a radical, almost scary idea back then?
That was the huge, uncomfortable question his work raised. And the reaction initially was largely disbelief and resistance. Many prominent scientists of the time, including Chandrasekhar's own supervisor, the famous Sir Arthur Eddington, and even Einstein himself, found the implication that a star could collapse indefinitely towards infinite density simply too repugnant or absurd. They felt something must intervene to stop the collapse. Nature wouldn't allow such a thing. Eddington publicly ridiculed Chandrasekhar's result, and Chandrasekhar was even discouraged from pursuing this line of work further for a time. It was a controversial finding that challenged the established views of stellar physics and cosmic order.
That must have been incredibly difficult for him as a young scientist. But history proved him right.
Absolutely. He was eventually awarded the Nobel Prize in Physics in 1983 for this groundbreaking theoretical work done decades earlier. It laid the foundation for our understanding of black holes. So, what does happen to those stars exceeding the limit? Building on Chandrasekhar's work, Robert Oppenheimer, later famous for his role in the Manhattan Project, and his colleagues did further calculations in 1939. Their calculations, using Einstein's general relativity, showed that if a star's core mass exceeded the Chandrasekhar limit, or the equivalent limit for neutron stars, gravitational collapse would continue relentlessly. The star's own gravity becomes so incredibly strong that it warps the fabric of space-time around it dramatically.
Like a giant, super heavy bowling ball placed on a trampoline, making a really deep, steep dent.
Yes, but even more extreme. So extreme that the very paths that light can travel get bent inwards. General relativity describes this using light cones, which represent the future paths light rays can take from any event. Near a collapsing massive star, these light cones get tilted inwards by the intense gravity. Eventually, if the star collapses within a certain critical radius, called the Schwarzschild radius for a non-rotating star, the light cones tilt over so much that even light emitted directly outwards can no longer escape. It's dragged back by gravity.
Light itself can't get out.
Exactly. And since nothing in the universe can travel faster than light, if light can't escape, nothing can escape. This region of space-time, from which escape is impossible, is what we call a black hole. The boundary of this region, the point of no return, is called the event horizon.
The event horizon.
Yeah.
So if you cross that boundary, maybe in a spaceship, there's literally no going back. It's like stepping onto a one-way path from which no signal, no message, not even a beam of light can ever return to your friends or family waiting outside. That's truly chilling.
It is a profound concept. From the perspective of an observer watching safely from a distance, as a star collapses to form a black hole, the light from the star would appear to get dimmer and dimmer, and also redder and redder, as the light waves lose energy climbing out of the intense gravitational field. It would seem to take an infinite amount of time for the star to actually cross the event horizon, fading from view completely. All that would be left is a black hole in space, exerting its immense gravitational pull but emitting no light of its own.
What about this cosmic censorship idea I read about? It sounds very dramatic, like the universe is trying to hide something embarrassing.
It does sound dramatic. It's a hypothesis proposed by Roger Penrose. It essentially suggests that the infinitely dense points, the singularities, which general relativity predicts should exist at the center of black holes, as also at the Big Bang, are always hidden from outside view by an event horizon. In other words, singularities are never naked. They're always clothed by an event horizon. This is important because at a singularity, our known laws of physics break down completely. Predictability fails. Cosmic censorship, if true, ensures that this breakdown is contained within the black hole and doesn't affect the predictability of the universe outside the event horizon. It keeps the universe orderly, preventing weird things like potential time travel paradoxes that might arise if naked singularities existed and could influence the outside universe.
So the universe tidily hides its points of breakdown behind a curtain of no return.
Okay, so if a black hole is basically just this region of no return defined by gravity, what does it actually look like from the outside, other than black? Does it remember what kind of star it used to be? Does it have any distinguishing features at all? This leads to a truly fascinating and remarkably simple result known as the no-hair theorem. This idea was developed and solidified through the work of several brilliant physicists, including Runner Israel, Brendan Carter, Roy Kerr, and Stephen Hawking. It essentially states that in the end, a stable black hole has no hair.
No hair, like a bald head. What on earth does that mean for a black hole, an object in space? Is it just a catchy phrase again?
It is catchy, but it has a precise meaning. It means that once a star collapses to form a black hole and settles down into a stable state, almost all the complex information about the original star, its chemical composition, whether it was lumpy or smooth, its magnetic fields, all the intricate details, all that hair is radiated away or swallowed, effectively lost to the outside universe. A stable black hole, according to this theorem, can be completely characterized by just three external properties: its total mass, its total electric charge, which is usually assumed to be zero or very close to zero for astrophysical black holes, and its rate of rotation, its angular momentum.
Only three things: mass, charge, and spin. That's it.
That's it. All other details are forgotten. If you know those three numbers, you know everything there is to know about the black hole from the outside. If it's not rotating, it's a perfect sphere, as described by Schwarzschild's solution. If it is rotating, as described by Kerr's solution, it will bulge slightly at its equator, like a spinning top that's a bit flattened, and it drags space-time around with it.
So it's like throwing a really complicated detail painting or maybe an intricately carved sculpture into a shredder. All the original detail is gone. All that's left is the total weight of the shredded paper or wood chips, maybe whether they're electrically charged, and how fast the shredder was spinning when it finished. That seems like a huge loss of information about the original star.
Yeah.
How does that impact physics?
It is indeed a profound loss of information, and it has huge implications for fundamental physics, particularly related to thermodynamics and quantum mechanics. The famous black hole information paradox stems from this. Does the information truly vanish forever, or is it somehow preserved or encoded in ways we don't yet understand? That's a major puzzle. But from a practical standpoint, the no-hair theorem hugely simplifies black holes. Despite the complexity of the star that formed it, the final black hole state is incredibly simple, making them mathematically much easier to model and predict their behavior.
Okay, they sound incredibly weird and simple, yet complicated. But how do we even know these things actually exist out there if they're invisible, black, and maybe lost all memory of what they were? It feels like trying to find a black cat in a pitch-dark room during a power cut after a big Diwali celebration. You can't see it, maybe you bump into it.
That's precisely the challenge, and your analogy is perfect. We can't see them directly. Well, not their insides anyway. But just as John Michell guessed way back in 1783, black holes still exert immense gravitational force on anything nearby. So we have to look for their effects on visible matter or light that passes close to them. We look for the gravitational bump in the dark room.
What kind of effects? How do we see the gravity of something invisible?
There are several key lines of evidence. One of the earliest strong, albeit indirect, clues came from observations of extremely luminous objects called quasars. In 1963, an astronomer named Martin Schmidt was studying a faint star-like object called 3C273. It was known to be a strong source of radio waves, but its visible light spectrum was baffling. Schmidt realized the strange pattern in its spectrum was actually the normal pattern for hydrogen, but hugely redshifted. This wasn't a gravitational redshift from the object itself. It was a cosmological redshift due to the expansion of the universe. This meant 3C273 was incredibly far away, billions of light years.
So it looked faint only because it was ridiculously far away.
Exactly. And to be visible at all at such an immense distance, it had to be intrinsically unbelievably bright, emitting more energy than hundreds of entire galaxies combined, all from a region not much larger than our solar system.
How is that even possible?
The only plausible explanation physicists could come up with for such an astonishing amount of power coming from such a compact region was the energy released by matter falling into a supermassive black hole at the center of the host galaxy. The intense gravity accelerates infalling gas to incredible speeds, heating it up and causing it to radiate immense energy before it disappears across the event horizon. This suggested the existence of monster black holes, millions or even billions of times the mass of our sun, lurking at the hearts of these distant active galaxies.
So essentially supermassive black holes at the centers of these galaxies, acting like cosmic engines, gobbling up gas and stars and shining incredibly brightly as they do.
Exactly. That was a major pointer. Another crucial piece of the puzzle came, again somewhat accidentally, in 1967 with the discovery of pulsars by Jocelyn Bell Burnell, who was then a research student at Cambridge. She detected these incredibly regular pulses of radio waves coming from specific points in the sky. They were so perfectly regular, like clockwork, that at first they jokingly nicknamed the source LGM-1 for little green men, half wondering if it might be signals from an alien civilization.
Little green man? Seriously?
Well, briefly and jokingly. But they soon realized these pulsars were actually rapidly rotating neutron stars, the other possible super-dense endpoint of stellar evolution for stars not quite massive enough to form black holes.
Okay, but neutron stars aren't black holes. Why was their discovery good news for the theory of black holes? How did that help?
Because neutron stars are themselves incredibly extreme objects. They pack the mass of a star into a ball only about 10 or 20 kilometers across the size of a city. They are unbelievably dense. The discovery of pulsars provided the first concrete observational evidence that stars could indeed collapse to such incredibly small, dense states, just as theory predicted. If nature could make neutron stars, which are only maybe a few times larger than the critical radius needed for a star to become a black hole, it wasn't such a huge leap of faith to imagine that other, more massive stars could collapse even further, crossing that final threshold to become black holes. It proved that extreme gravitational collapse was real.
Right. It showed that such incredible densities were actually possible in the universe. And then there's the famous case of Cygnus X1. This is often cited as the first really compelling, specific candidate for a black hole, isn't it? What makes it so convincing?
Yes, Cygnus X1 is the classic example, often considered the first really solid observational evidence for what we call a stellar mass black hole, one formed from a single star. Astronomers often observe binary star systems, two stars orbiting their common center of mass due to their mutual gravity. They're very common. In the Cygnus X1 system, astronomers saw a large, bright blue supergent star, but they observed that this star was orbiting very rapidly around an unseen companion. Something massive had to be there, gravitationally pulling on the visible star, but emitting no visible light itself.
Okay, an invisible dance partner.
Exactly. Furthermore, this system is also a very strong source of X-rays, detected by early X-ray astronomy satellites. The best explanation for both the unseen mass and the X-rays is this. Matter, gas, from the outer layers of the visible blue supergent star is being gravitationally stripped off and pulled towards the unseen companion. As this gas falls inwards, it doesn't fall straight in. It forms a swirling disk around the companion called an accretion disk.
Like water spiraling down a drain.
Precisely. As the gas spirals faster and faster in this accretion disk, friction heats it up to millions of degrees Celsius, causing it to emit those intense X-rays that we detect right before the gas takes the final plunge into the unseen object.
So we can't see the black hole itself, but we see the incredibly hot, glowing gas spiraling into it, like a giant cosmic whirlpool with an invisible drain at the center. That's how we see it.
That's exactly how we infer its presence. And here's the clincher. By carefully observing the orbit of the visible blue star, how fast it's moving and the size of its orbit, astronomers can use Newton's laws and Kepler's laws to calculate the minimum mass of the unseen companion pulling on it. For Cygnus X1, the calculated mass of the unseen object is at least 6 times the mass of our sun, probably more like 10 or 15 times.
And that's crucial because...
Because, according to Chandrasekhar's result and our understanding of neutron stars, this mass is far too large for the unseen object to be a stable white dwarf. It's also significantly too massive to be a stable neutron star. The upper limit for neutron stars is thought to be around 2 to 3 solar masses. Therefore, the only known type of object that could be that massive yet completely invisible and consistent with the X-ray emissions is a black hole. The key insight is using the behavior of the visible star and the X-ray emissions to deduce the properties of the invisible companion, ruling out all other possibilities.
So Occam's razor points straight to a black hole. Despite some lingering bets among famous physicists, maybe it's pretty much accepted now.
I'd say the confidence level among astronomers is extremely high, well over 95%. While scientists always explore alternative, sometimes more exotic explanations, a black hole remains by far the most natural, simple, and robust explanation for all the observations of Cygnus X1. And since its discovery, even more compelling evidence has accumulated. We now have strong evidence for many other stellar mass black holes in binary systems throughout our galaxy. And we also have overwhelming evidence for those supermassive black holes at the centers of most large galaxies, including our own Milky Way. There's one called Sagittarius A star, right at the heart of our galaxy, about 4 million times the mass of the Sun, that we see stars orbiting at incredible speeds.
Mind-blowing. What about really tiny black holes? Could they exist, or do they always have to be formed from the collapse of massive stars?
That's a fascinating question. Theoretically, yes, much smaller black holes could exist. They're called primordial black holes. These wouldn't have formed from collapsing stars because a star with such low mass, say the mass of a mountain or even less, can easily support itself against gravity forever. Even after it runs out of fuel, it wouldn't collapse. But primordial black holes could potentially have formed in the incredibly extreme high-pressure conditions of the very, very early universe, just fractions of a second after the Big Bang. If there were regions that were spontaneously much denser than their surroundings, the immense pressure of the early universe could have squeezed them directly into black holes, bypassing the need for a star progenitor. Whether these actually formed, and if any survived until today, is still an open question and an active area of research. And intriguingly, as Stephen Hawking famously predicted, due to quantum effects near the event horizon, smaller black holes are actually expected to evaporate or radiate energy much faster than larger ones.
So tiny black holes might actually glow.
Paradoxically, yes, they might not be entirely black. This Hawking radiation means that very small primordial black holes might actually be quite bright in certain types of radiation, potentially making them detectable, although none have been definitively found yet. But that's perhaps a deep dive for another time. Hashtag outro. So today we've really journeyed through millennia of cosmic discovery, haven't we? We went from believing Earth was this flat, central stage for all creation to understanding our true, perhaps more humble place in an immense, dynamic, expanding universe that appears to have sprung from a colossal Big Bang about 13.8 billion years ago. We've seen how brilliant minds, stretching from the ancient Greeks like Aristotle to pioneering Indian scientists like Chandrasekhar, to the giants of modern physics like Newton, Einstein, Hubble, Hawking, and so many others, have tirelessly challenged existing ideas. They use logic, careful observation, powerful mathematics, and bold theories to peel back the layers of cosmic mystery. We explored the fascinating life cycle of stars, their birth in collapsing gas clouds, their long lives balancing gravity and nuclear fire, and their dramatic deaths, leading sometimes to the formation of incredibly dense white dwarfs, neutron stars, and ultimately the ultimate cosmic enigma, black holes. These objects are so dense that nothing, not even light, can escape their gravitational grasp once past the event horizon. Yet we can infer their existence through their powerful gravitational influence on the stars and gas around them. It's really a remarkable testament to the power of the human intellect to probe and understand the unseen.
It truly is incredible when you stop and think about it. All these vast, almost unimaginable cosmic events. The Big Bang that started everything, the galaxies rushing away from each other in expanding space, stars collapsing under their own weight, these mysterious invisible black holes devouring matter. They all seem to be governed by the same fundamental laws of physics that we experience right here on Earth. The same laws that make an apple fall from a tree in Kashmir or make water swirl down a drain in Kerala. It's all connected. It really makes you wonder, doesn't it? If we've managed to uncover so many incredible secrets about the universe, its beginning, its expansion, these bizarre objects in just the last few centuries of scientific inquiry, what other mind-boggling truths are still out there? What mysteries are waiting just beyond our current understanding, waiting for curious minds like yours to ask the right questions and figure them out? So the next time you look up at the night sky, maybe after a long day of school or work, or perhaps when you're celebrating a festival like Diwali with your family under the stars, just take a moment. Remember that you're not just looking at a random pretty pattern of twinkling lights. You're witnessing the grand ongoing story of a universe that began with an incredible bang, continues to expand and evolve, and holds secrets far more profound and fascinating than we can currently even imagine. What question will you ask the universe tonight?